In this video, we're going to be continuing on with our series on TensorFlow that makes use of Keras to build a very simple regression model to, in this case, predict miles per gallon for a given car based on a number of features like cylinders, displacement, etc. Just to very briefly recap what we've done so far, we've captured the miles per gallon dataset from this website. We've downloaded this into our script. We've figured out what the feature names are, read that in, and then what we've done is done a little bit of analysis on the data, just some very cursory observations. So we dropped any of the data set that happened to constitute any values that had NAs just to remove them. We took the origin variable or feature, and what we did with that, it was previously a unique number that was encoded as 1, 2, or 3, each of those being a number denoting where the car originated from, so USA, Europe, Japan, and we created a one-hot encoding for each of those features for every single car, for every single value that we have in our data set. So for instance, for a given car, if the number here is 1 and the rest are zeros for this, these three features, this would indicate that this car originated from the US, and so on. The other thing that we did is we split the data set. So we took 80% of our data as training data and 20% as our testing data. And what we did then is we explored the data both visually and also both in a more text-based way. So we created a pair plot using Seaborn to just get a quick visual about how these features compare to one another. And then we also looked at some of the just very basic statistics of the data that we have. So the mean, standard deviation, etc. So we took a look at how the data is structured just to kind of get a better sense of what we're dealing with. In this video, what we're going to be doing is we're going to be actually building the regression model, and we're going to be using Keras and TensorFlow to do that. And hopefully at the end, we'll have something that's able to predict fairly accurately the miles per gallon of a car based on these features. Before we get to that, I just want to do a little bit of house cleaning, and that is the way in which we split the data. The way in which we do it here is we use this .sample function, and this is fine, and I just want to change this just so that the type that we get back is a little bit different. So I'm going to use a function from sklearn, which is a train test split function, and it does the exact same thing. It splits the data based on some criteria that you specify using a random seed. The only thing that's different is the type of variable that is returned, and the reason I want to use the sklearn thing is just because it makes the rest of what we're going to be doing in this video a little bit simpler and I think a little bit easier to understand. So what I'm going to do is I'm just going to comment out these two lines, and then at the top of the file I'm going to go ahead and import sklearn's train test split function. So I'm going to say from sklearn.model selection import train test split. So I'm just importing this one function from this module. And actually, if you don't have the sklearn library installed, what you can do is you can just say pip install sklearn in your command line, and that will go ahead and use pip to install sklearn. I assume if you have TensorFlow and things like that, you probably already do have it installed, but in case you don't, that would be the line that you run to get it on your machine. So assuming that you have that, let's go ahead and change these lines so that way they're updated with the train test split function that we've just imported. So we're going to, again, do the exact same thing as to what these old lines did in a different way. So I'm going to go ahead and use a little bit of a different terminology as well. Generally, in a machine learning context, you refer to your entire data set, both train and test, before you split it as X. This is a matrix that just constitutes the variable names as well as their respective values, and then the corresponding thing that you're trying to predict, which is usually denoted as lowercase y. This is just a vector of values that corresponds to the training label. So in this case, what we're trying to predict is the miles per gallon. So we're going to go ahead and use that convention. You'll see this often in other machine learning contexts, whether it's textbook or something that's more applied like a piece of code. So I'm going to say X is equal to, in this case, just the data set. And again, X is the matrix that corresponds to the entire data set with the exception of the thing that we're trying to predict. So I'm going to go ahead and drop that from our data set. So I'm going to say X is equal to dataset.drop, and then I'm going to specify the columns that I want to drop as the miles per gallon column. And the next thing that I want to do is construct the Y variable, which again is just a vector that corresponds of just the miles per gallon vector. So I'm going to say this is equal to dataset, and then the only thing that we're going to do here is it's just equal to the MPG miles per gallon part of the data. So it's kind of the complement of what we just did for x. So now that we have that, let's go ahead and split our data. And what we can do is make use of this train test split function that we imported up at the top from sklearn. And this function returns a tuple of 4 items, 2 of the first ones being the train and test data, and the 2 remaining ones being the train and test labels. So they're all split, and they're split in a way where the x test, x train are the labels for that data, and then I should say x test, y test, that data corresponds to that label, and then x train, x test, y test corresponds to the respective data and labels for that. I'm just going to write it out because I think probably what I said was more confusing than it probably should have been. So I'm just going to go ahead and say x underscore train, comma, x underscore test, comma, y train, y test. And this is equal to the function that we imported. So train test split. This function takes a number of things very similar to the things that were passed into this function here. We specify what our data set is, in this case it's x, what our training label is, which in this case is y. We want to specify what size the test data is going to be, so you can specify that by saying test size. We specified before the training size to be 80%, which means the test size is 20%, so I'll go ahead and put in 20% for the size of our test. And then we also can specify a seed, which is going to tell how we want to sample from this data set. So if you hard code a seed, this takes the same sample every single time you run this, which allows you to reproduce your results as opposed to just randomly sampling from the data set. In a more applied context, you'd probably want to remove the random state. This is really just for reproducibility, so you can actually run this and kind of get the same results to see what's happening. But again, you probably want to remove this when you actually build your model. So I'm going to go ahead and get rid of that extra space. And now we've gone ahead and effectively split the data set up. So I'll go ahead and remove those lines. The next thing I'll just do a little bit more housekeeping. I'll remove these plotting lines. I'll remove this for now, remove the training labels. And then again, just more of a little bit of a recap as to what we did before. We had this normalize function, which calculated how many standard deviations away from the mean a given value in our data set was. And then we normed our training and test data set. And this again allows us to kind of be agnostic to the units that we use for the data that we're using to build our model. And this allows the model to essentially train itself better and be able to perform better optimistically. So I'm going to get rid of these lines because we're not norming train data set and test data set anymore. We're doing this on the newly created xtrain and xtest variables that we created up above. So what I'll go ahead and do is I'll say xtrain is equal to norm xtrain. So I'm just normalizing the training data for xtrain, and then we'll do the same thing for xtest as well. So now we have normalized training and testing data. So the next thing that we can do now is actually go ahead and build our model. So the model we're going to do is I'm going to create a function, which is just going to be called build model. And the reason I'm wrapping this in a function is just for kind of later purposes. We might want to go back and tweak this, and having it wrapped in a function is just going to make the whole process a little bit more streamlined and easier to modify a little bit down the road. So let's go ahead and create that function. We'll say def build model. And then what we're going to do here is we're going to actually fill in the function. So I'm going to create a model object using Keras. So I'm going to say model is equal to Keras.sequential. And then inside of here is where we're going to define the layers of our model. So we're using the sequential model that is going to have 2 densely connected hidden layers and 1 output layer. And that output layer is going to return a single continuous value. That single continuous value is going to hopefully correspond to the miles per gallon of a given car, given what the model is going to predict for us. So I'm going to go ahead and create the 2 hidden layers first, which are just going to be densely connected layers. So I can say layers.dense. Inside here, I'll say that there's 64 neurons. I will specify the activation function to be a ReLU function, which is fairly typical for these types of problems. And then we can specify what the input shape is. Now the input shape is going to be the size of the number of features that we have. So this we can just get this by simply saying x.keys, which are going to be the elements or the names of what is present in our data set. So I'll go ahead and say input underscore shape is equal to length. I'll wrap this in a list, length of x.keys. So that's all we really need to do there. The next thing I'll do is I'll create this second hidden layer as a dense layer as well. So layers.dense 64 activation function will be the same. And then the last layer is going to be the output layer, which again is just going to be a layer with one output neuron, and that's going to correspond to the miles per gallon prediction. So here I'll say layers.dense and then an output of 1. The next thing that we want to do for our model is specify an optimizer. I also notice I have a typo here. This should be Keras. We want to specify an optimizer. So I'll go ahead and create an optimizer object. So I'll say optimizer is equal to, and this is something I'm going to take from the Keras library, tf.keras.optimizers. And for this particular optimizer, let's use RMS prop. And you can specify a number of parameters for this particular optimizer. One of the ones that I'm going to hard code here and pass in is the learning rate. And I believe it's already set as a default for this value. I'm just hard coding this to kind of make it a little bit more explicit. But if you check the documentation, I'm pretty sure the learning rate by default is already set to this value. So it's probably redundant, but there it is. The next thing that we're going to do is actually compile the model. So we can say model.compile. And then here we're going to specify what our loss function is going to be for this model. And in this case, what we're going to be using as loss function is MSE, or mean squared error. For the optimizer, which is another parameter that this takes, we're just going to pass in the optimizer object that we created up above. And the last thing are the metrics. And this is just a list of essentially things that we can use to specify how good the model is doing. And the metrics that we're going to use are going to be MSE and also MAE. So that's mean squared error and mean absolute error for the metrics. I think that's metrics like that. The next thing we're going to do is just return the model. So that's pretty much it. Keras makes this very simple to actually build our model in TensorFlow. It's very high level in terms of how we're actually building this. And the next thing that we're just going to do is just create a model object from this function. So we're going to say model is equal to build model. I'm going to get rid of this last line down there. I'm going to go ahead and make sure that nothing blows up. Let's go ahead and say Python part 3, run it and see what happens. So we're going to run this. Hopefully nothing blows up. If it does, we can just figure something out. And it looks like the model object was successfully built. We don't see any output because we're not printing anything, but we don't see any errors to indicate that anything we did in the build model function that we called upon is incorrect. We got some output from the previous videos. This happened to be in the normalized data that we happen to see there. So it looks like the model is built successfully. So now what we want to do is actually go ahead and train it. So let's go ahead and try to do that. So the way that we can do this is specify how many epochs or essentially iterations we want the network to train for. The more epochs, the more time and computational resources you'll need. For this video, we can probably get away with maybe 1,000 epochs. For the sake of time in the video, I'll probably just specify 100 and then scale up as needed. But let's just go ahead and create a variable that will be called epochs, and we'll set this equal to 100 for now. So how many iterations the neural network is going to run for. And now what we want to do is we actually want to fit the model. So we actually want to run it. And the way we can do that is we can just say model.fit and feed it in the training data that we want to fit the model to. And this function actually returns something which also corresponds to the history, and that is how the model is performing on each iteration or on each epoch that it's being trained for. So I'm going to go ahead and return that, and I'm going to say history is equal to model.fit. Model.fit takes a few arguments, one being the training data, the training label, and then also, of course, how many epochs we want to train for, which we specified up above. The validation split is another optional parameter that is also taken here. So I'll say validation split is equal to 0.2. And then I'm going to specify another optional parameter, which is verbose. And this just tells this thing to output more than it needs to. So if verbose is set to 0, you don't get any output. It's just kind of makes the output a little bit more clean if you have a lot of things going on. I want to see what's happening here, so I'm going to set that to 1 or true in this case. Okay, so let's just go ahead and see what we have here. So I'll say print history once we're done with that. I'll write this and then run it, and let's just see what happens. So we should see a lot of the same stuff that we saw before. Let's see here. So name train stats is not defined. Problem I think I removed when I was doing the housekeeping, the train stats lines, which we need to keep for the normalization function. So just go ahead and put those back in. So train stats, in this case, we have to change it a little bit, is equal to x underscore train.describe. And then we'll say train stats is equal to train stats dot transpose. This is pretty much the same thing that we saw before. Let me just get rid of that highlight. So all we're doing there is just like we did in the previous video, we created a table using the .describe method that gives us a high level view of all of the statistics of the training data. And then I just transposed it because I want essentially the columns to become rows and vice versa. And then that is what is being used in this normalization function. Okay, so that is everything we need there. So let's just go ahead and try and run this again. I'll clear the terminal to get rid of that error from before. Let's write this and run it, and we'll see if we get, so it says data form, okay, so transpose. So I think so I think I spelled transpose incorrectly here. Transpose, try and run this again. So let's see what we get. So now we have it actually training, and that was very quick. We had 100 out of 100 epochs already trained. As the model goes along, it happened pretty quickly there, so I'm actually going to increase the number of epochs to, let's just say 1,000, so we can discuss what is happening as this is actually going on. As it's going here, we have a loss function, a mean squared error, and then these are kind of the things that are going to be hopefully going down as the model continues to train. So as the model continues to train, it gets better acquainted with the data. Hopefully there's some aspect of it doing better. Sense as to what is actually happening by just looking at the textual representation of the training for that model. What are the things that we can do to get a little bit of a better sense as to how this model is actually faring with respect to the training and validation data sets is by visually looking at it, by graphing something. So what I'm going to do is I'm just going to copy and paste over some code that I have off screen here, which just plots the history object that we created. So I'm just going to put a space between the code that we have not changed, the code that we were working with, and the code that I copy and pasted on over here. Basically, this is just a function which takes that history object that we constructed, and it just plots two things. So on the x-axis, we have the epoch, and then the y-axis, we have the absolute error, which again is our metric for loss. Absolute error with respect to how it's predicting the miles per gallon training label. So let's just go ahead and plot this, and I'll kind of describe what we're seeing as we call this function. So I'll write it, I'll clear the terminal, and then I'll just say Python part 3. So what we're going to see is the model training itself, again, for 1,000 epochs. This shouldn't take terribly too long. And again, we can see kind of as it goes here, the loss function is going down, which is what we want to see. And we can kind of see visually what this corresponds to and whether or not we should be trusting this representation. So what we see here is a graph where the orange line is how the validation error is faring across the epochs. So the x-axis is here, and then the mean absolute error, the metric that we're using to determine losses on the y-axis. So we can see that the blue line that denotes training data is steadily going down across all of the epochs, which is good. However, the validation is not. So at this point, around the 100 epoch or so mark, it seems to be pretty stagnant. It's not getting any better, even though the training data is getting better. So this is probably an artifact of overfitting. We're overfitting specifically to the training data that we have. The model is not generalizing well. It's not generalizing to our validation set, and therefore it's not able to predict general values or general entries from our validation set. So we need to figure out what is happening here and how we can mitigate this problem. So what I'll go ahead and do is suggest the following thing. One thing we can do is we can make use of this early stopping metric. Basically what this is, it's a built-in piece of functionality in Keras that makes use of something called a patience parameter, which is the amount of epochs to continually check for improvement. And if it sees no improvement, no further improvement is being made, it kind of prematurely stops. So let's go ahead and use this early stopping criteria within our model. So I'll go ahead and build a new model. Again, this is kind of why we put it into a function, so that way we have a way to construct a new model without any of these other things that we've been doing in between. And then I'm going to go ahead and create a early stop parameter. So I'll say early stop is equal to keras.callbacks.early stopping. And this takes two parameters. What do you want it to stop on? So in this case, we want it to monitor or early stop on the var loss. You can check the keras docs for other parameters that you want to feed in for this variable or for other variables if you want more information on that. But we want it to stop early if it's not getting any better on the loss function. And you can also specify a patience metric as well, which I think by default we can just specify to be equal to 10. So now that we have this early stop parameter, we're going to again construct this history object. So I'll go ahead and copy this history object, put it down here. And now, in addition to the things that I've added here, I also am going to add another parameter, which is a list of callback functions. So one of the callback functions, obviously, that I want to put in here is the early stop callback function that we've created up above on line 112. So say callbacks is equal to a list. In this case, the list only has one object, which is the early stop parameter. So now using this, and I'm going to make sure that I don't do that one. I'm just going to go ahead and comment this out as well. And we'll keep the epochs at 1,000. I suppose we don't need to build the model twice, so we'll go ahead and comment that out as well. So we've got our plotting function, and we're constructing the model using the early stop, and then we're constructing a new history to see if we actually get a different story based on this early stop parameter here. So we'll say Python part 3. Oops, Python part 3. And it shouldn't train for as many epochs as we had suggested it to train for, which is 1,000, because at some point, as we saw from the previous graph, it didn't get any better past a certain point. And indeed, the early stop parameter, notice this, we see the training data goes down nicely along with the validation data. And then past this point here, there doesn't make any sense for the model to continue training because any of the benefits it goes from further epochs are going to be not really going to be taken advantage by the model. It's not going to add to any of its predictive power. So it early stops or it cuts off at around 100 epochs. So that's pretty much it for this video. If you have any questions, comments, suggestions, improvement suggestions for how I deliver this content, please let me know. The code, as always, for all of these videos is going to be available on my GitHub. Majority of this tutorial was based on a very nice set of TensorFlow documents provided by the TensorFlow people at Google, and the link for that is provided in all of these videos if you want further information on how they go about it. I put my own twist on this and did kind of my own thing to make it a little bit, I think, not better, but different. Hopefully it conveyed some of the information more optimally for you. And again, if you have any suggestions for other videos in this topic, please let me know. Thanks again for watching, and I'll see you in the next video.